Good afternoon. So I have good and bad news. The good news is that there will be still a test tomorrow at 4 o'clock. The bad news is that this will be the last lecture here on observing techniques. And of course, Ignacio just reminded me, because there are many more topics that have to do with observational or observing techniques like astrometry. But well, we only had 7 lectures, and we had to spread it over some topics. And I think we covered a lot of different things already. So this is certainly not everything, but I think you heard about many things that maybe you were not familiar before. But today's topic is spectroscopy, and I think this is something you should be more familiar with already. Who has never heard about spectroscopy before? Okay, I'm asking it this way because no one puts up the arm, so that means we all know about spectroscopy. Yes. Good. Okay, nevertheless, I think I'll start as usual with a simple introduction. Then we talk about the general principle of a spectrometer, about some of the dispersing elements, gratings, filters, and so on, different types of spectrometers, the shell gratings, very thorough spectrometers, and also some even more advanced concepts. Because, well, as we will see, there's one limitation of an object of a spectrometer. With an imager, you get many images of many sources. With a classical spectrometer, you get the spectrum of one source. And since the sky is full of interesting sources, many astronomers are not happy with that anymore and want to make the time more efficient at the telescope. So there are many more spectrometer concepts around now at big telescopes that use a lot of the fact that we have in parallel multiple spectra. And then I'd like to say a few words at the end of the analysis. Okay, so let's start with a basic reminder, reminder on astronomical spectra. So, I mean, this is, I think, really trivial, you all know this. So if you have a black body, simple black body, you get a continuum spectrum in all colors. If you have some object like an H2 region, for example, relatively thin gas, which is highly excited, then you get lots of discrete lines here on top of a relatively weak continuum. And of course, you can also have a continuum source in the background and some foreground gas that is absorbing at, for example, these discrete wavelengths, energies. So then you get this absorption line spectrum. And we don't, for most of what we discussed today, we don't care whether it's absorption or emission line spectrum. Spectrographs work for everything. And why is it so important then? Because, I mean, continuum is nice, we can make color diagrams maybe, but a lot of the physics is really contained in the lines. This is just a plot from the Sloan Digital Sky Survey showing some templates of different galaxies. So you have a boring galaxy like our own. Then you have some galaxies here with emission lines. We just look at one famous emission line. What do you think this one is? One has an idea. If you look at the wavelength here, it's a bit more than 6,500 angstroms. Sorry? Yeah, and hydrogen. H alpha. What is H alpha? Does everyone know? We'll get back to that on the next spectrum anyway. Right, so with the hydrogen energy levels, you have the different series, meaning that from well, if you have the hydrogen atom, and here you have a set slate, you have the first energy level shell, second, third. And then if you have an excited electron falling back on the first one, then of course you have the Lyman, depending on where it's coming from. You have the Lyman series. If it's falling, combining to the second shell energy level, then you have the Balmer series. This is not named after Steve Ballmer from Microsoft. Anyway, so if it falls then from the third to the second, it's the first transition to the second, so you call it alpha. And we're from the second to beta and so on. And the Balmer series is also called just simply H. So H alpha, here H alpha, we know it's a transition from the third to second main level, energy level of the hydrogen atom, and this corresponds to a wavelength of, I think, 665 nanometers.
6563. Very easy to remember.
Okay. And this line actually, and there is, I mean, so you get some information from these spectral lines, of course. One information you can get is the line flux itself. Obviously, if it's brighter, there is more, higher, let's say, there is more photons contributing to that emission. So that means that there is more excitation of that line in the object. And H alpha, for example, is often used as a tracer for star formation activity. So if you measure that line and you can calibrate it because you know how far your galaxy is away, then you can, for example, derive the star formation rate. But then the line shape is also relevant because here, we look here at the broad line QSO and it's called there is a broad, it's the same line essentially, but you see it's a lot broader. This is not just the density, right? This is because of dynamical effects. So you see the line broadens dynamically due to the rotation or the dynamics in the nuclear region of this QSO. Okay, so that means you have gas there with thousands of kilometers per second velocities toward and away from you, and that's just broadening the line. Okay, so, but in order to build a spectrograph, of course, we need to know what wavelengths we want to build for. And so we should remember there are many transitions. You know, in all kinds of systems that can contribute to very discrete wavelengths, emission and wavelengths. What I've drawn here is the hydrogen atoms, of course. These are electronic transitions, which change the principal quantum numbers, like the Lyman values. And they contribute, well, obviously here in the visible range. There are also fine structure transitions, which are due to the energy levels, not the principal quantum numbers here, but due to energy levels between the electron spin and the nuclear spin. And typically, the energy in these transitions, of course, is a lot less. And remember, the energy is the product of the Planck's quantum times the frequency. So if the energy is less, the wavelength is longer, and we observe these lines typically in a bit different. Go.
Pues dependiendo de la transición, ya sea actividad, pues descendente o ascendente, es una línea de emisión o de absorción, ¿cierto? Entonces, mi pregunta va a que, bueno, la línea de
Very interesting.
I can guess what you're asking.
Oh, very good. 2 weeks in Colombia. Well, the question is how the absorption lines, the Barber series absorption lines are produced since the electron is in the first level. It's not, the atom is not excited.
Yeah. Well, let's look at two scenarios.
This was what you understood.
Yeah, sort of. But I thought before I give the wrong answer to something that wasn't asked. Okay. Let's assume you have a hot gas, right? That's easy. So you have hot H2 region, HEN, whatever, right? So you have an atom here with a surrounding shell, and because of the thermal energy or the input from elsewhere, it gets lifted to that state and somehow excited, and it recombines, and the radiation will be emitted in all directions, of course, right? And then if you're observing from here, you see this on top of some, let's say, continuum from the region itself. Okay, now what's happening? Let's say we take our quasar now, or whatever source that provides the energy here. So again, light will pass through. And here now, let's say we have a cool cloud of gas. Okay, there is hydrogen gas, of course, hydrogen in there. And now our excitation photons, the ones that have the right energy will excite the hydrogen atom here. So it's in principle the same process. It will excite the atom, and so it will jump from the second to the third shell, and it will eventually recombine and fall back. Now if it would fall back and continue in the same direction towards us, there would be no change, right? We would not see an absorption line. But of course, the recombined photon here could be emitted in any direction, right? And so these are all the ones we would miss. We only see the ones that go there. And so geometrically, we only see a very small fraction of the electrons that get excited and recombine in this cloud. And so we will still see a lot of the continuum light from here that's just passing through our gas cloud. But then we see at this wavelength, which is exactly the same as what is needed to excite the atom, we will see this. We have the continuum, and then we see the absorption line, because we're missing all the light that gets now taken out of our line of sight and emitted in other directions.
Yes, but all of this is assuming that the atoms are in the second level. The question is how they get there. How they get to the second level? They are not in the first level.
Yes, well, these are our recombination lines typically, right? So if you have an ionized atom, it may jump back. So you do not have all the energy only at that level. So you will also see other hydrogen lines. Okay? Not sure. This is
not sure. I think that the heat from the gas pumps many atoms to the second level. Statistically, they are normally all of them are in the first level, but statistically, many of them are temporarily in the second level and absorbs the Barber's series of lines.
So the line ratios that you see,
the H alpha absorption magnitude is.
Yeah, I'm thinking of a nice diagram to show you. Let me do that maybe tomorrow with the podcast, because I think this is very fundamental. I thought this is well known, so I did not prepare anything here. I used this actually for explanation rather than this. So the other, okay, we have fine structure transitions, we have hyperfine structure transitions, which are now the interaction between the magnetic moment of the nucleus and the magnetic field of the electron. And that produces lines that are seen in the radio, for example, the famous 21 centimeter line, which is the main probe of the neutral atomic medium in the universe. And then we also have molecular transitions, because like here it's all atomic. But if we have molecules, it's not so easy anymore with the simple Bohr's model of the atom. In this case, the molecular transitions are also quantized transitions, but now the molecule may rotate or vibrate, so that it's the structure, the atomic structure of the molecule itself that counts. And there are rotational transitions, which mean a change in the angular momentum of the rotation of the molecule, or vibrational transitions, where a molecule with several bonds, it may internally vibrate. And many of those require a dipole moment. So if you have molecules without dipole moment, then it's difficult to observe them. For example, molecular hydrogen is such a problem. And there are nuclear lines, which are energy level differences in the nucleus. And you can imagine that these require a lot of energy. So they're observed at very high energies, 15 keV, and they're only seen in X-ray or gamma ray. And then you have transitions in solids as well, in ices. So this is when it gets in the dense, cold interstellar medium for a star formation, for example. And I think that's relevant here. And of course, if you combine all these, some of this information, then it tells you a lot about the object. For example, the continuum. If you look at, this is a radio galaxy, 3C435A, meaning simply that it's the 435th object in the third Cambridge catalog. And so this is the bottom left here, you see a continuum map where most of the emission comes from the center. Right? These are the radial lobes of the galaxy here. And if we go to an O2 map, we don't really need to know what the energy is, but you can, I think you believe me, that O3 is a transition that requires higher energy than O2. And there are some distinct differences here between those maps. And so by studying the maps, you learn a lot about the energetic processes in the galaxy. Okay, so this was just the appetizer. Now, how do we measure it? So the principle of a spectrometer is relatively simple. You need the slit. There's a hole missing. So onto which the light of the telescope is focused. Here. You need the collimator that uses the diverging light and collimates it. And we'll see later what actually, if you don't know already, what a collimated beam is. And then it's the collimated light is hitting the grating or any dispersing element, which spectrally disperses now the light out. First, this is the key component, but of course with all the rest around it, it would not work either. And then at the end, of course, we have to report. So these are our four main components, and the grating here sits usually in the pupil. So again, you have a re-imaging system, right? Imagine your star is at infinity over there, and you have a telescope maybe somewhere here. So the telescope is in the pupil. And then your telescope focuses the light from the star and creates an image here. And at the focal plane of the telescope, where the image is, This is where you put the slit. And the purpose of the slit simply is to select a small part of the image. And then this colimator here produces an image of the pupil. Now again, the pupil, we said, was given by the telescope that we put here. So this is actually, if you would put a camera here, you would actually be able to see the telescope. Not the stars, but the telescope. You would really see just the mirror of the telescope. And this is where we put the grating. So the grating is at the pupil, at the same optically, again, the same place as our telescope is. And then we have the light focused again on the Sorry? The collimator, oh, you can. I think it could be a lens as well. But any optical element that focuses, any optical element with power. Only that if they had put a lens here, I would be off the screen, right? So they put a mirror there so that you can fold the view. But generally, it doesn't matter whether you use lenses or mirrors. But you just need something here to. Okay, and we'll see why actually. If you don't put an optical element here, you will not get collimated. The image products. So let's say this is a simple spectrum. What's this? Maybe now is the time, Marco, to introduce your ingenious gadget. Well, first, okay, let's say do you have a grating at home? Who has a grating at home? Or something that's sort of a grating?
Maybe this?
This usually works pretty well as a grating.
Do you have this? Okay, so you can ensemble a very simple spectrogram with this using pieces of CD. Okay? So I will pass the whole thing and you take the pieces and give to combine.
When you assemble it, not during the lecture, please. When you assemble it, you will essentially have a configuration like this without that part. So we're missing the collimator there because it has to be simple. And this camera lens, this is essentially your eye. Right? This is the pupil of your eye, and it's focusing it here on the retina, and your brain is here. When you assemble it, this is how it looks. So since don't expect you to build it in real time. In fact, you shouldn't. So I'll pass this around, and you can actually look through it. You need a bright light, of course. Look at the light. Okay, the light comes into this hole here, and then we glue down a little piece of the CD, and then you see the reflective, spectrally dispersed light. So this piece of CD is really put here. Sorry. You have to look through the big hole first. This is the small thing. So, okay, but yep. So you should at least see broad bands of green and red and blue. Okay. So if we do this now, the principle is the same, but if we do it in a bit more sophisticated way, we can build our astronomical spectral graph. And this is a typical image of an astronomical spectral graph. So these are so-called long-slit spectral graph. When I'm discussing here different spectral graphs, I'm just showing for illustration some of the data products, meaning that this is what your detector will report. so maybe you can help me to explain what we see here. Okay, so on this axis here it says constraints. So that's probably the wavelengths. On this axis here it says arc seconds. So that's probably some spatial information on the sky. Just relative angle with respect to field. So if you think about this with a slit, in what direction here would be my slit? Okay, so I mean there are only around two possibilities, right? So one possibility is that the slit would be oriented this way, and one possibility would be that the slit is oriented this way. So who thinks it's oriented this way? There is no third possibility. So at some point I want to see all your arms because I can tell you the slit is not oriented this way. Okay, so who thinks it's oriented in this way? Yeah, just for checking. Who thinks it's oriented in this way? There are still some undecided. Okay, so what do? We essentially have an object on the sky. Okay, say we look at the full moon, and then we take a slit. Yeah? So we take, let's say, we take the slit, narrow slit here. So that means that we will never get a spectrum of the left side of the moon or the right side of the moon. We will just get this spectral information on the central slit. But for all of these field points here, we get a spectrum. And it's usually should be oriented such that it's spectrally dispersed then in this direction. So this point here will have a spectrum. And this point here will have a spectrum. Like that and so on. Right? So this is what we see here. So we have the range, the spectrum here. That means that our slit was oriented this way. So along here you see, well, not surprisingly, but this is listed in arc seconds, you see different points. So this is the center of the object. And yeah, so this would be then just 50 arc seconds to one side, 100 arc seconds away, and so on. And what we see here is, okay, now maybe we can already see what this galaxy is telling us. Again, this number should remind you of something I just erased from the board. We can already identify one of the spectral lines here, namely page alpha. And we said 656, so we can count 0, 1, 2, 3, 4, 5, 6. Okay, so there is no line. So that already means that our galaxy is slightly redshifted. Okay? And of course, it's written here anyway, so we're looking at a nearby galaxy called M83, so it's the 83rd object in the Messier. And okay, so we see that the central region of the galaxy is obviously the brightest part, because it has the strongest lines here, emission lines, but it also has strong continuum emission. Right? So the galaxy obviously gets fainter when you go away from the nucleus, which is not a big surprise. But then we can also see that some of the lines have a slight tilt here. Right? The line is not really straight. It's here, and then there's a little tilt here, and then it continues here and slightly. Any idea what this might be due? So the tilt here should be due to the Doppler shift, the rotation of the galaxy. And then we have also lines here, like this one. I hope, can you turn it off for a second, please? The light. Oh, great. So if you look carefully, you can also see a line here that looks pretty straight and is not getting brighter in the center of the galaxy. What could that mean?
Maybe absorption or something, or
There's telling me.
nearby, so from the own atmosphere or something.
Exactly. So if you remember our first class, right? The atmosphere is not our friend. It will, well, astronomical. It will add a lot of signatures to our signal here. It will add general background, but it also has very discrete emission lines. And this is one of them. And so it's not surprising that it doesn't get brighter in the center of the galaxy, because of course the atmosphere doesn't know what galaxy we're looking at. So you can already, by just looking at the spectrum, say, okay, there is a lot of H-alpha emission, and it has a bright nucleus, and the atmosphere. It's also nice that you have, actually sometimes it's nice to have these lines, because at some point you need to wavelengths calibrate the spectrograph. You need to know, I mean, of course now we know this is 656 nanometers, because someone has kindly put these numbers there. But of course if you read out the detector, the axis labels are missing. So at some point you have to calibrate it and need to know what wavelengths it is. But you know at what wavelengths these atmospheric lines are, and so you can use them actually for calibration. But this is a typical spectrum, say a galaxy. A raw spectrum, right? At some point you have to extract that information and make a nice plot so that it looks like a spectrum we're familiar with. Okay, so the very basic characteristics of a spectrometer are, of course, its spectral resolution. Or some people call it the spectral resolving power. And it's defined as the wavelengths divided by the minimum wavelengths, or the narrowest wavelengths interval you can resolve. Where delta lambda, this interval is called the spectral resolution. And the way the line looks like, again, if this is a very narrow atomic transition, there are no thermal broadening, whatever Doppler shifts involved. Usually the lines are very narrow, but you will still find something that looks more like a Gaussian profile. And that is simply because usually the line is broadened by your spectrogram. Will not resolve it intrinsically narrow. And now many of the things we have been discussing for imaging a point source, and you get an Airy pattern out. There is of course some analogy in the spectroscopy as well. If you had an extremely narrow line, you observe it with a spectrograph. It's not the same process, but it's the same formalism you can use to describe it, namely the line shape that you observe. Okay, can you turn on the light again? Okay, that's a very simple example. Nature provides you with an energy transition, and so you would have no emission. You would have one discrete line which corresponds, say, to your H-alpha. Yeah. And now you're running through the spectrograph, so your black box. And what you observe then is something like that. And that has a finite width. And the broadening here, okay, so let's say this intensity distribution would be the initial one, it's a function of frequency. And what you observe here, that's the observed one. And the observed one is simply a convolution convolution here of the intrinsic line shape, the initial one, convolved with the transmission of your spectrogram. So the line, instrumental profile. So what you observe is the convolution of your intrinsic line shape convolved with the instrumental profile of your spectrum. And then, of course, we remember that if we want to have a spectrograph and build a spectrograph that gives us this information, if you have a spectral line like that, you should design it optically that your line width is at least, sampled by at least 2 pixels. Now, remember, the Nyquist theorem says that in order to learn that there is such a line, you need to sample in 2 pixels. If you have higher demands, if you want to know more about this line, remember before we said in an HEN where we have very broad lines, if we study the line shape exactly, then we learn a lot about the dynamics. If you know maybe about P60 stars, there's a lot of physics that you can derive from the line width. So then the line doesn't just look like that, but there's a lot more information in the line shape. But first, if you want to resolve then those details that are in the line shape, then you need a better resolution and more pixels. Okay, but in the simplest case, this is what I should use. And then finally, an important part is the transmission of the spectrograph, which is a very important one because if you want to take the complex spectrograph can have transmissions maybe as low as 10%, meaning that you lose 90% of your light due to all kinds of diffractions, scattering, efficiencies, and so on. So it's really an attempt to make this number as high as possible because, well, remember what if you lose 9/10 of your light, you have to square it in terms of observing time. Right? This is the signal. If you lose the signal, then your signal to noise drops, and you have to compensate it by integrating length longer. And this is certainly not what you want to do.
What about this instrumental profile? It is related. Okay, of course, it will be related also with the size of the copy, and it will also relate with the properties of the grading.
In the dispersion direction, so it's actually to a large extent independent. Now, of course, along the slit, where you have your spatial information, right there, the angular resolution, where the pupil is important. In dispersion, it only matters the design of the spectrograph. So essentially, if you have we look through our can explore our spectrograph. So, and well, you see some lines, but they're very broad, and that's because it's not a perfect spectrograph, right? So this profile, this instrumental profile here of our homemade spectrograph, is pretty bad. No? You can, of course, look at the same lamps with a professional spectrograph, and your line width it would be much narrower and would have a much nicer shape and everything. So that then, if you're integrating with higher resolution, higher spectral resolution, then your instrumental profile should also be narrower. So the equivalent, you can make this analogy to the telescope, the equivalent to your telescope diameter is now the resolution, the spectral resolution of the grating. So before we had the telescope determining the angular resolution, right now we have the grating determining the spectral resolution. Because remember, we take a spectrum only from essentially my picture of the full moon where you put the slit across, right? You take only the information from a field point in the center of the slit. Your slit is very narrow. So across the slit, you usually lose all the spatial information, but you keep it along the slit. So that's why the spectrum always is a one-dimensional image as well.
Also, the finite size of the slit could alter the resolution, the frequency resolution, because you can get light from neighbor comets and get some.
Yes, yes. Designing the right slit width is non-trivial. It has to do with the wavelength. But then, obviously, when we have a spectrograph, we want to look at different wavelengths. So in principle, you could only make it really optimized for one specific wavelength. So it's always a compromise, and you always have to deal with. Okay, but can I say spectral resolution? Again, I said here, many lines in the universe are very narrow. Now, from galaxies that are usually in extragalactic astronomy, doesn't really need very narrow, doesn't have very narrow lines in very high resolution spectrographs, because most galaxies are big, they're moving fast, and that all contributes to a broadening of the line. So by the time the light reaches us, if you have light from the left part of a rotating galaxy, it may be redshifted, from the right part it may be blue shifted. You combine all that line, and it just broadens light, and it just broadens the line. If we look at galactic regions, often the lines are very narrow. And then the question is, what spectrograph shall we use if we have very narrow lines? And this is a simulation. A simulation of a spectrum, this is actually a molecular spectrum of C2H2 and HCM, two gases at degree 900 and 600 degrees. If you have a spectrograph that gives you the resolution of 2000, right? Remember here, the resolution 2000 means that, okay, in this case, let's the numbers again. Let's say we have a wavelength of 12.8 microns, and it's hard to compute that. Let's say you look at 10 micrometer wavelengths. If we look at 10 micrometer wavelengths and we have a resolution of 2000, what's delta lambda? Sorry? Well, if lambda is 10 micrometers and R is 2000, what's delta lambda? Well, obviously it's 10 micrometers divided by 2000, right?
10,000 is 5.
5 nanometers, is that? Okay. So delta lambda would be 5 nanometers. So that means roughly the width of our line, roughly speaking, this would be corresponding to 5 nanometers in this case. Right? So because if the line width, that's very similar, like, again, it's not exactly the same, but it's not so much different from the Rayleigh criteria. Where Lord Rayleigh said, well, we can distinguish between two sources in imaging if they're separated by whatever 1.22 lambda over 2. And in this case, we can resolve. That's the spectral resolution, of course. We can resolve two lines. So if there is another line here, I can resolve it if the other one is offset by something like the width of that line. If that line would be much broader, I would never be able to tell that there are two different lines. So the line width in micrometers or nanometers with respect to the absolute wavelength, that tells you how the resolution of your spectrograph is. Okay, so lambda over delta lambda is we take intrinsically narrow lines, meaning that they're not broader than our instrumental profile, P of frequency. And this is for a resolution of 2000, and you can see that, I mean, it's an absorption line, let's say. And so you have the continuum here, and you have a weak absorption here, and another weak absorption here. And you can imagine that if this were a noisy spectrum, you can almost overlook that there's a line. Now, if you had a high resolution spectrograph, that's not taking the average anymore. And you have very discrete absorptions here. And you can see that you get two things. You get one, you get, well, they're obviously more pronounced. You can see them more easily, right? So they're at higher signal to noise. And you get additional information because suddenly you see, oh, this is not just one line, there are several ones. And of course, that tells you about the relative ratio between those lines. Tells you something about the temperature of the gas. So this is essentially information. And again, I'd like to make the analogy to the imaging case. For imaging, we said if you take a bigger telescope, you have essentially more sensitivity and you get more information, spatial information, more detail. And in this case, it's almost the same for if you use higher resolution spectroscopy, you get a better signal to noise on the lines, and you have more information here. You have more delta lambda, like in the case of a big telescope, more angular resolution. Okay, so this is the two things are actually not so much different in the character. And this is, of course, the reason why many people prefer high-resolution spectrographs, but they are not for free, like big telescopes are not for free. So let's look first at some of the elements that we need for the spectrum. Okay, we already know one, right? That's our CD here. Not sure if I can hold that correctly, but maybe some of you can see from the distance here. Spectrum. And so let's look at the grating here. Essentially, we need a device that for our beam introduces simply an optical path difference between different rays. And so we do this here. This is our grating surface, and here we have, as you can see, we have little steps. Now consider there are two rays coming in, ray 1 and ray 2. And they're being reflected here on this surface of this one step. Back. And then the fundamental grating equation says that if we have constructive interference, we'll get light in this particular direction if for these angles of incidence and reflectance, alpha and beta, times A, where A is the separation of the grooves, right? This is the structure on the grating, of course. Well, gratings can be made in different shapes, surface shapes, but it's always a regular pattern of some variations. And the period of these variations is then, or the distance between the grating grooves. Grooves is the channels that someone etched in or grooved. Is A. And so if this A times sine of the incoming angle plus sine of the angle of the reflected beam, if this is a multiple of the wavelengths, right, M is just an integer number that is essentially the order of the diffraction, then you have constructive interference. Okay, I think you have not seen this for the first time. What I should point out, however, is that we assume here that ray 1 and ray 2 are parallel. This is probably not given when we look in our homemade spectrograph. Right? Because obviously, if I look at the lamp far away, the light is dispersing, and the rays that are hitting the grating are not necessarily parallel. best performance for the spectrograph you'll get for in the previously sketched figure if you have a collimated beam. And collimated simply means that the rays coming from the same object point. In this drawing, right? Remember, I just recycled one of the drawings from the optics lecture. If your rays here are parallel from the same object point, now if you take another object point, let's say here, they will have a different angle, right? They will not have the same tilt. They will have a slightly different angle, but again, they will all be parallel. And in this case, it's called collimated beam. And if you put a grating in the collimated beam, then the resolution of the grating, or the resolution that the grating will provide, or essentially the depth that you can expect here for your spectral line, which determines the resolution lambda over delta lambda, is given by m times n. And m, again, is from the previous grating equation, the order, and n is the number of illuminated periods of your grating. If you want a really high resolution, you need to have many groups illuminated by your beam. Right? There is no way in this picture that you say, oh, I use a very tiny grating and then I only have 4 groups. I quickly made it myself. I have 4 groups and I expect it to have a resolution of 100,000. No way. In order to get high spectral resolution, you need a lot of groups that contribute to your interference. That makes the grating large. Yes?
The grating device would be or
well, gratings you can make of many materials. Right? In the end, you only need the surface of this. So
I think if the grating is regular, alpha and beta must be equal because the level.
oh yes, in first order, yes. So there is n here, and that's the order of diffraction, and we'll soon see that it's not always good to use it in first order. In the simplest case, yes, you're right.
But not, because this says have an limitation, so alpha and beta are not equal but are related with the angle of the.
Yes. I mean, yes. Well, I'm not sure if I shall explain it here or on the next slide. You have
The grade is the normal to the structure of the grade, but not the normal to the surface. Right?
correct.
Because otherwise it has been the grating must be triple.
No, this grating normal is the normal to the. It's not the normal to the grating surface. But we'll discuss a couple of cases where this is not the case, and maybe then it becomes clear. Yeah, I mean, if it's not, please ask again. So, okay, high resolution means either m high or n high.
Little announcement. No se vayan ahí. Al final me voy a tomar fotos por valientes. Again. Just because I want to take a picture at the end of this class, because this is the brave people.
Oh.
The brave that withstand the thunderstorm.
You'll take a picture, not the spectrum.
No. Because the writer's models are paralyzed.
Okay. Now there is also in this case, of course, this only tells us that this is the requirement to get constructive interference. But in fact, you have an interference pattern. It's maxima and minima and maxima and minima. And so the light is actually reflected in various angles that are not always the same. And so generally the energy of the beam that you shine on the grating is diffracted by this periodic structure in various orders and directions. And so if you pick out only one arbitrary order, this is very inefficient because you lose most of the light. And there is one requirement, and now we come back to where we don't talk about the grading normal, but the normal to the surface, tilted surface of the individual groups of the gradient. And you can imagine that if you have the incoming beam at an angle which is the same as the outgoing, the reflected beam, with respect to the normal on top of the surface of the group, then this process is very efficient, and this is called the place angle, or you can gratings that are operated in this condition are called place gratings. So the reason to do that again is because in this condition most of the light is preferentially reflected than in this direction. And you have a high efficiency, meaning that most of them will not. The disadvantage is that in principle, if we don't worry about efficiency, then we just look at here from this, we can look at it from all kinds of different angles, and we will always see spectra. So the advantage, of course, is if you don't care about the efficiency, you can turn it around, you can take whatever grating you have. If you want a very high efficient grating, you should operate it to satisfy this condition, but that means that you have to match the sign of your grating exactly to the design of your spectrograph, so that you really have the optics then such that the light goes in here and comes in here and gets reflected here. Okay, so the place angle here of the orientation of your groups already defines how you align the grating. Now there is one problem with many spectrographs, most spectrographs, which is the free spectral range. I mean, this is just a light bulb looked at through a transmissive grating. Of course, you can imagine that it would not be a reflective grating, but it would be transmissive, where the grating still would work because you have a denser material, crystal, some glass that provides them an offset in the optical path difference, and the light that gets through will still interfere. So in this case, you have the zeroth order, the light gets straight through the grating without much in the center, and then to the left and right you have two orders. This is the first plus and minus first different order of diffraction. So far, so good. Unfortunately, this image here is cut off from Wikipedia, but there is also a second order here, and the third order here, and the fourth order here of this grating. So the higher diffraction orders. And the problem is that the distance between these orders is getting smaller and smaller, and the dispersion is getting bigger and bigger. And so they overlap. And this is illustrated here. So let's say you have to shine light on the grating. You have the specular reflection, so that gives you first and your zeroth order. This is here. And then to the left and the right of that, satisfying the grating equation, you'll find the spectrum like with here, right? -1 plus 1. First one minus first one, just reverse. Now, the second order is here. And you can already see in this drawing here, not obvious here, but in this drawing, that they're overlapping here. So if you put a screen here and you image it, because I mean here obviously this is your spectrum, right? This is what you want to record. If you image it, the problem is that if you observe something here, you don't know, is it really a line at in this case lambda 2 of the first order, or a line close to lambda 1 of the second order. And it gets worse and worse when you go to higher orders. Okay. So the free spectral range, meaning that you will get pure spectrum from only one diffraction. Free spectral range is the largest wavelength range for a given order where there is no overlap in the same wavelength range with an adjacent. Okay, so it's only the difference between the maximum and minimum wavelength. And that free spectral range is the wavelengths divided by the order. And you can see if you just broke yourself, if you go to higher orders, they're all overlapping. This is a problem. I mean, now at first you might say, what's the problem? Then I don't go to higher orders. Right? Would be a simple solution. But remember what we said before here. The resolution of the grating is given by the product of diffraction order and the number of groups. If you want a really high resolution spectrograph, as I said, first, you can observe in first order and just take, well, there are 1 million groups. Okay, but obviously it's all applied for diffraction like anything. We must not forget the wavelengths. So if we want to have a grating operating at 1 micrometer wavelength, obviously we cannot take grooves smaller than 1 micrometer. Right? Because the light will not see the grooves anymore. Anything that's small compared to the wavelength, the light will ignore. And that's the same reason why we don't have to polish radio telescopes. There is a small crack or scratch, smaller than the centimeter waves that we observe. The light does not care, and the radio telescope works. We go to shorter wavelengths, optical telescopes, we need to polish them very clearly. So that's and scale smaller than wavelengths. Now, for the gratings, of course, we want to have the opposite. We want the light to experience the grating. So if we want to have a grating that works at 1 micron, we have to make the grooves bigger. I don't know, let's say 10 micrometers. Okay. So let's say we have 10 micrometer groove size. And we want to observe in first order, and we want the resolution of 1 million. Right? We're ambitious. That's a bit much, but okay, let's say 1 million. So what's 1 million times 10 micrometers? 10 meters. Okay. So you build a spectrograph with a resolution of 1 million. You need a grating that goes from this wall to this wall. And you illuminate it. Yeah, that would be challenging. I think no one has ever done this. But there are spectrographs that have extremely high resolution. So one solution is to not observe in first order, because if we take a very higher number, then of course the grating shrinks accordingly. Let's say we could make it the 100th order. The grating would not be 10 meters anymore, but just 10 centimeters. Okay? And suddenly we have solved the problem. Well, I mean, we would just need our 10 centimeter grating, and we still use our 10 micrometer grooves and illuminate the grating. But now we're not looking in first order, but we're looking at an angle somewhere here in 100th order. And we can design a grating that's very efficient so that most of that light is actually transmitted in this 100th order by following this place angle equation. So that means that we have to build, we can't just use the CT here, but we have to design how the grating looks like. This is called, I hope this is the next slide. Let me go here and then back. Sorry, I'm flipping slides. And this is called an Echelle grating. So an Echelle grating is a grating where you don't actually shine the light from the top, but from a very, very small angle of incidence. So let's say we have our grating again here, right? You can imagine how the grating surface looks like. So this is the grating surface. And so then onto the grating surface. And we have it, this is our blaze angle here, theta. And if we want to make it really efficient, we actually record the light that goes back in the same way, specular reflection. But then you have to keep in mind that, I mean, this is only one ray from the same object. We will also have a ray coming in this way, hitting that part of the grating, going back and interfering with the light going back from here. So you essentially, you cheat a bit with nature because you add a lot of path difference here that is larger than normally the grating constant. And, well, I mean, I can explain that forever. I hope you get some idea. So the point is, you use a very small angle or high angle of incidence here with respect to the grating normal. So coming here almost horizontally, hitting the grating grooves from the side, and you get interference now between that groove, wall, edge, and that one. And in the best case, you have the maximum efficiency in this configuration if your incoming beam is the size of the direction, almost the direction of the. Okay, and this is how the so-called shell grating works. If you go to very high resolution spectrographs, they're usually always using these shell gratings. And they're then operated at diffraction orders, the order of 50 or even higher. So this is why I was so keen on the free spectral range, because this in principle would be a problem. And so how can we get rid of the problem? We now know how to, in principle, get very high resolution. Right? We take a big grating and operate it at very high diffraction order. But we still haven't solved the problem of the order overlap. Because if you record a spectrum here, the spectrum of the 50th order overlaps completely with the spectrum of the 49th order and the 51st order and so on. And that wouldn't count, right? Then you get a spectrum, but you cannot calibrate it. So what do? There is an order.
This is the type of spectrometer used in the search for expands, right?
Exactly.
This helps history.
Exactly. So what Greg is referring to is that one way to find exoplanets is, well, you can't see the exoplanets themselves, but the planet and the star are moving. I mean, the planet is not moving around the star. Both are moving about their common center of gravity. And so because of the gravitational pull from the planet, the star is also moving around the center of gravity, meaning sometimes the star is approaching us a bit, and sometimes it's going away from us. And so if you have some emission lines from the star, and you observe them over some time, you can see them changing in wavelengths. So sometimes they're a tiny bit blue-shifted, sometimes they're a tiny bit red-shifted. And this is the velocity. I mean, we're used as in astronomy, especially astrogalactic, 1,000 kilometers per second. But if we look at the velocity of the star that's introduced by the planet, right, it's about this. Right, this is how the sun moves because of Jupiter or the Earth. Right, so this really just a few meters per second. And in order to see that tiny shift, you need to have extremely high spectral resolution. And then you need an initial spectrograph. And in order to avoid that the orders overlap, one thing you can do is to use a pre-disperser. So, and this is, I haven't found a way to fix that. I mean, can you see on the slides that there are a few boxes drawn around here? Now on the handouts? No, sorry. No. So,
yes, they are this. Okay, I have
not in the copies.
This is my original.
Sorry. Okay. Anyway, the point is you have a grating here. Dispersing. Okay, this is So you have, let's say, different orders. The different orders only have a relatively small wavelength range. Just to say 50 nanometers or something like that. Relatively small. And so your red order would be from here to here. And it overlaps with the yellow order from here to say here. Right? Sorry, it's just over right. Then the green order, they're all the same length. It would be from here to here. And the blue order from here to here. And you want to separate them. Because they all coincide, they lie on top of each other. And the way to solve this is by adding another dispersing element, like a prism, just before that. And that element is 90 degrees rotated with respect to the dispersion direction. So you have a so-called pre-dispersion. And again, we said there is very tiny spectral delta lambda in this direction here. But the pre-disperser is a relatively large dispersion here that separates different wave bands. And so we have these orders spread in space. We still have the order 50, 51, 52, 53, but they're not on top of each other anymore because we have an additional disperser here. We have stretched them in wavelengths in the other direction. So that's the trick people play by using pre-disperser. Okay, this is not immediately obvious. You have to think about it. But you can also just put down a couple of wavelengths if you like, and based on that you say, okay, from here this is whatever 100, this is 200. So at this point here would be 120. So then this is the point of 120. So you have the dispersion here between 100 and 120 or something. You can look at it. You can also, you find a lot of that information very nicely explained with graphs or so on the internet these days. So if the slides are not sufficient, I encourage you to just browse the internet, maybe starting from Wikipedia, where I took many of the figures. Okay, so this is where we've been. So now we know how to get to high resolution. And not everyone needs high resolution. So we can also use low resolution. And of course, I assume you know what a prism is. So I didn't even put a slide there to show a prism. But there is one device that you find in many, many cameras and sort of spectrographs at astronomical observatories. If you want a low resolution spectrum, up to a few hundred, maybe even a few thousand. And that's called a prism. And the name implies that it's a prism is a combination of a transmission grating plus a prism. Now, why would one do that? Let's say you have the light coming in this way, and then you have, this is of course only for one wavelength, but the prism would give you then some dispersion, right? Some light this way, some would be less diffracted, and so on. Some blue light more refracted. Okay. And then at the other side of the grating of the prism, you put a grating, some grating surface. And that acts as a transmission grating. So that acts in exactly the opposite way for the optical axis, essentially. And if you dimension the two well, require some calculations, but it's not too difficult. Then you have a spectrograph, you have some because the effects, they don't cancel each other in terms of dispersion. They only cancel each other in terms of refraction of at some wavelengths. And that means that, as you can see here, the optical axis here, and the direction of this beam, ingoing and outgoing, is essentially the same. And that makes it a very, very popular device to get dispersion. Because imagine you have a simple imaging camera. And that's the next slide. Maybe if you have if you want to do reasonable astronomy with photometry, you have to have a well-defined pathband. You put a filter there. So most cameras have in their pupil plane a filter wheel that allows you to select filters. So you say, I want to observe the band or the B band, because then I can construct a vertical Russell diagram. Okay? So most cameras have a filter wheel in the pupil that allow you to select the spectral filter wheel. And with this device here, you can also put it there. And you would also have the light transmitting in the same region, but then at the end you will get, for each point, a spectrum. Not just a broadband filter image, but the spectrum, if you put in the prism. If you would just put the grating in the filter wheel, well, the grating would, of course, refract the light in a completely different direction, and it would never reach the detector. Right, so the prism is a dispersing element which can be practically implemented like a filter. And that makes it quite nice. Now, of course, well, this I was already referring to. You find transmission filters in almost all imaging cameras. And then, of course, you have, the principle is not much different. You have a series of interference layers on some substrate. And so you have the interfering conditions, which in the case of the filters can be satisfied over a relatively large waveband. This is just an example of a set of 4 filters. And the point important here is that, of course, no filter is perfect, right? You would like to have for a filter a complete rectangular function with a well-defined cut-on wavelengths and then 100% transmission across the waveband, and then sharp edge and 0% transmission outside of your passband. But in reality, filters often look like that. So transmission here, wavelengths here. This is a broadband filter over a couple of microns, and you can also see that the transmission is often relatively bad, depending on the wavelengths you're working with. But again, transmission filters also require some interference between layers, and therefore they're also small spectrographs, but you will not get to the spectrum at the end, you will just get the broadband image. You can make that, of course, by using different substrates and different layers there to change these interference conditions. You can make them also as narrowband filters. Right? If you, for example, that's the difference to the grating. Why would you want to use filters? Well, my stupid example of the full loop where you put a slit across, right? You would only get information of points along the slit. Right? You would not see 99.99% of the full moon. If you're, say, interested in H-alpha emission from the moon, I do not recommend this because there's probably not an H-alpha emission from the moon. Why should there be? But if you want to try it. But then, of course, you can take a narrowband filter, some filter that only lets the very narrow band that includes the H-alpha line pass through. But then that filter, that of course you can take a whole image. So you trade in spectral information for spatial information. Okay, now there is one, of course, this has a limitation here because the interference layers are fixed by design and the resolution of filters is typically only a few hundred. You can bring this to higher resolution when you use the so-called fabric-Perot technology. And the fabric-Perot is essentially 2 plane parallel plates of extremely high precision that are brought very close together. And you shine the light in at some angle, and the light gets reflected back and forth. And then the same as before will happen here. You have under some angle and for some wavelengths. And now you can tune with the distance between the plates, you can tune the wavelengths to have this interference condition satisfied. Mainly the transmission band that you get through is maximal if you have 2 times the distance here is a multiple of the order of the diffraction. There are many things that could be said about the Fabric-Barreau. So this is for very narrow, high resolution spectroscopy of narrow lines. But you will not get, you can put a detector here and you would get an image of the source. But you will get it only for one distinct wavelength. So this is an imaging spectrograph, if you like. But if you want to have a spectrum, you have to take many images, changing the distance between those plates, between each image. Right, so then you have a series of images, each one shows a different wavelength. And, well, maybe, okay, so that the performance characterization of that Fabric-Barreau, I was about to say let's skip this, but then I realized that this may be a question of the test form, so I should mention it. Okay, so the performance of this Fabric-Barreau, how well it's doing, is characterized by a quantity called the finesse, which is defined as a function of the reflectance of these plates. So sorry if this may be confusing because I've overused R. Before R was resolution. Now I'm talking here about the reflection. So high reflectivity and sorry, this maybe I should have used a small r here or a capital R here. R here. This is not resolution. This is reflection. Sorry. Okay, and then the spectral resolution, essentially the width of the line. Right? Remember this plot here. That you get spectral resolution of the Fabric-Barreau is given again by the order that it's operated in times this term in this. Of course, reflection means that you have to polish it very, very precisely. If you take quantum mechanics classes actually somewhere at the university, you can start discussing with your professor in quantum mechanics how the Fabric-Barreau works, because classically it's not so easy to understand. Because on one hand, we want maximum throughput from here to here. On the other hand, we want to have maximum reflectance here, so that the light has the maximum number of reflections back and forth, so that essentially no light gets out here again, but it's always reflecting and interfering. And to combine the two requirements, I think this is not classically explained. So this is a different. Okay.
The question. So the spectral resolution is not dependent on
Here.
this.
Well, it's implicit in the order. I think. Like this is the quantity. This is the quantity that's given by the actual device, the Fabric-Barreau you have. Like you order it from some manufacturer, and you'll get it. It's a good Fabric-Barreau. It has a finesse of say 50 or so. But then, yeah. Okay. For the remaining 20 minutes, I'll try to be possible. I will show you a couple of spectrometer constants. Now we know the different ingredients, and now this is now again some pretty pictures of different spectrometers you'll find at observatories. There is one important category, which is becoming more and more important actually, are multi-object spectrometers. Oh, actually, maybe you can turn off the light again, please. Yeah, so what you essentially do is, if you, I should have told you to turn off the light. Okay, let's assume.
That's why we put away this.
Sorry. Okay, so so let's say you're an extragalactic astronomer. You look at the Hubble deep field, and you have lots of galaxies. Yeah, lots of galaxies. Now we take our simple slit spectrograph. Now you put it somewhere. We could even say that to determine what angle we're looking at, but in this case, let's say if we can take the slit this way, right? And then remember the spectral dispersion would be perpendicular to the slit, so we'll get a spectrum of that galaxy. You get a spectrum of that galaxy. You get a spectrum of part of that galaxy. The problem is we're still missing out on most of these galaxies. And you can say, well, then you have to go back and put the slit there again. The problem is that getting good spectra of galaxies at high redshift, you have to integrate there for 1 night, 2 nights, whatever. So if you want to study galaxy evolution, if you want to study how the early galaxies evolved, so high redshift meaning faint objects, and you cannot not explain how galaxies evolve by just looking at 2 or 3 of them. And so, well, if you need 2 nights per object and you want to study 5,000 to 10,000 of them, then you're busy with it for the rest of your life. And you will never get the observing time anymore. So you want to use some spectrograph. Actually, most of that information here is not necessary, right? I mean, this is empty sky here. This is empty sky. This is empty sky. So you waste most of the information along the slit. So now the idea is, why not construct a spectrograph where we just use this location here, and this one, and this one, and this one. So then we don't have a continuous slit, but we just pick out part of the focal plane. And this is shown here. This is now a hectospect. I think it's an instrument built by the Smithsonian and in Boston and Cambridge. Let's say you have the focal plane of the telescope here. And then in the focal plane of the telescope, you have these tips here of these, there are these little sticks that are sticking in here. Right? And at the tip of these sticks, you have either a tiny mirror or at the end of a fiber, and that picks out the light from just one galaxy. So you need to know exactly where you're looking at. Yeah, you make a chart of your, I mean, let's say you know the Hubble deep field of Earth very well, you know where your galaxies are, and you say, I'm going to look at it with my telescope, and I know these are the coordinates of all my famous, my favorite galaxies that I want to get a spectrum of. And then you tell the computer to configure it in a way that the ends of all of these steps here coincide with the location of a galaxy imaged on that focal plane. So it's behind the telescope. In the old days, this was done differently. There was really the aluminum plate. You go to the old observatories, and then the day before your observation, you had to go to the machine shop. And then they made an aluminum plate for you with a couple of holes drilled exactly where you said, I want the holes here, here, and here. And then you had to put some fibers in these holes. And this plate was then put in the focal plane of the telescope, and if you did it right, that the light of all the galaxies was hitting the ends of one of the fibers. And so then the advantage, of course, is that instead of the slit now, I can just use the ends of the fibers, or let's think about fibers, the easiest case, and align them all together like a slit. Right? I mean, this is not yet the spectrograph, but I can now use that fiber here. I put the source here. I use the fiber and put the source here. Right? This fibers are flexible, right? That's the whole point. So here. You can see where this is going. Because now I have sort of like a slit again. I have all my sources aligned, and I don't have the wasted information in between. Okay, this is a typical spectrum of one of these MOS spectrographs. So you see, I mean, they're not aligned anymore in wavelengths. So they're offset with respect to each other. But this is a typical series of spectra, each one representing a different object from a MOS spectrograph. Multi-object spectrograph. There are other spectrographs, because before we said, example, Hubble deep field. We have here a galaxy, nothing, another one, and so on. So we wanted to have spectra of interesting objects from a large field of view, but we actually don't care much about, well, we would care, but we can't really resolve the galaxies anyway. So we just take a fiber that is just taking the integrated light from one of these galaxies. But we could also imagine that we had another interesting option, like, okay, what's an interesting option? A pre-made sequence star. Say, so we have the star here. We have maybe a disk around, right? Accretion disk. We may have some outflows. We may have some planets forming in the disk. This is all very interesting, right? So if we would take just a slit across, we would miss most of the information. Also, the multi-object spectrograph in this case wouldn't help us much. What we would really like to have is spectrum for each point in the field here. So all these squares, we would like to get a spectrum. And we can do this with this called the integral field spectrograph, where there are different ways to do it, but because in the interest of time, let me just look at one. The one at the bottom here. Let's say, let's imagine we would be able to slice the image, and just to cut it apart. I can cut a paper, and you don't have scissors here, right?
Right.
Do you mind if I toss my desk here? Okay. Say this is the field of view, right, of the spectrograph.
Ah.
Now, oh, excellent. Thank you. Now, this takes a while now. Okay, let's say if we manage to do this, what we can do optically is to cut the field and then take that part optically. That requires some optical scissors, and put it here. Take that part and put it here. Right? And you see where this is going. In the end, we end up with one long slit. And then we have something like our standard spectrograph. So, now how do we do this? The cutting, right? The optical cutting. Well, this is a device here, for example. If you put this in the focal plane, you can see this is a machine from aluminum. And these are the slices. So each slice corresponds to a slit, or will cut out this part of the image. So you place your entire image, you place on top of that, and it reflects one slice in one direction, and because they're all slightly tilted with respect to each other. And they will then be, when they're reflected in a plane somewhere here, they will then be actually offset with respect to each other. And so they're not next to each other anymore, but on top of each other. And so we have sliced the image, and then we send it to a spectrograph. And now we suddenly have, in one go, spectra for each of the field points here of a large field in 2 dimensions. This is a typical data product. So again, keep in mind that each one is a spectrum of one field point, but then you have different slices. You can reconstruct the image. These instruments, by the way, require So if you like to work on software, this is an area where you can maybe also find a job. And there are the shell spectrographs. And remember, a shell meaning high order grating, large grating, high order, and high spectral resolution. And this is shown here. So you have your collimator, so that the rays from the same field point are parallel. The collimator here, you have your shell grating here, and then the standard principle. Again, the point here simply is to show that the grating is really tilted extremely strongly with respect to the incoming beam. And you have another element here, the cross disperser, that makes sure that the orders are not overlapping. This is the optical system actually of existing. The shell is high resolution spectrograph in Criris on the VLT. It's shown here, so you can see this is the nascent platform of the VLT. So obviously the telescope mirror down here. The beam comes out here. This is the structure here from the telescope that supports the secondary mirror up here. And then at the side, connected to the port, you have this instrument here. That's Criris. And it just shows you that it's in reality you need a few more elements than the few that I just showed. But those are often just trying to fold the beam, because if you don't have these extra mirrors in there to fold the beam, your instrument would be gigantic. And this is actually, I mean, remember the groove shape here for our shell grating. So in principle, you would have some spectral reflection in this direction and also in this direction. And now look at this guy here who is inspecting the grating. You can see actually two images. Right? And this one image, that's the one directly up here. And that extended one, that's the image in this direction. And well, typical example of the shell spectra. Give me right here. So again, these are the different orders here. Thanks to our pre-disperser, they're not overlapping and coinciding. So, but they're spaced here. So that means that if you want to construct a complete spectrum, you actually have to put them together. So you have this one spectrum here, and then at the end of there, you have to get the other one here, and so on. So the total wavelengths, this is for a single object. Total wavelengths, total spectrum means that you then go from here to here. But of course, it's not surprising that you need all these orders, because, I mean, remember, we have the information about spectral resolution that's given by line width. And we have only a finite number of pixels here on our detector. Right? So if we have, say, if we only have 1,000 pixels across, that means we have 500 resolution elements in that direction. But of course, if you want a long spectrum, you have to cut and paste many pieces here. Okay, and now it would become really tricky, and I think we shouldn't do that, because if I now start explaining to you the Fourier transform spectrometer, we will not remember this course in the So it's a beautiful spectrum, because now Fourier transform is coming. That would be closing the whole course. And I don't remember if there was a question in the test. Right? And this is, I put this in parentheses, this is just a summary for reference, different types of spectrometers and their various advantages and disadvantages. And then finally, we should say that, of course, all that would not be, well, actually, we could not measure that. So if you get a spectrum to analyze, you have to somehow extract the intensity of the line from the data. And we usually do this by fitting the line either an absorption line or an emission line, typically a Gaussian. If it's determined by the Doppler shift or by the instrument Boltzmann profile. There are other functions for Lorentzian or Voigt profile, which is essentially the combination of the two. But you essentially, or if you have a very, very odd line shape, some say molecular absorption bands, you simply have to do a numerical integration, and that gives you the total line intensity. But one important name for quantity for all spectroscopy is so-called equivalent width. Have you heard this before? The equivalent width. Which is very handy because, well, the equivalent width is essentially just the width that your line flux would be, the integrated line flux would be in a rectangular window with respect to the continuum strengths. So it's essentially comparing the line intensity with the continuum intensity. And the beauty of that quantity is that it's independent of some things you may not know, like the distance to the object. If you just look at the line flux, you have just came back at the right time, Elena. Back to radiation transfer again. But this is the first time. So if you have some line flux itself, then you will, and you don't know the distance to the object, for example, the galaxy, then this will not tell you much. You cannot calibrate it. If you, however, express it in terms of the continuum emission, then, for example, if we think of the example we had before, the galaxy with H alpha emission, if we use the equivalent width, we essentially have a measure of how bright the H alpha line is with respect to the continuum emission from the galaxy. And so this is, of course, an important quantity that tells us about the activity of the star formation. And this ratio is independent of the distance, because if the galaxy were further away, the continuum emission would decrease in the same amount. So, but this was mainly to show you that people measure line fluxes equivalent width. But one important thing, so that's really the last thing, when you do it, when you extract spectrum, this is a real image taken from the Spitzer Space Telescope infrared spectrograph. And so you can see a couple of things here. Mostly you can see that not everything looks perfectly nice in terms of signal to noise. And of course, the spectra on the array, they don't follow precisely the pixel rows and columns. They're somewhere across the detector. And then they also have some profiles perpendicular to the dispersion. So how do you take the information? The easiest way would be to just cut out, you say in your software, you just cut out the pixels from here to here, and you plot, you have the program plot the intensity, and you get something like that. However, some pixels have more signal to noise, and the information is more useful. Others may be very noisy or have artifacts, and you don't want to include them. But you don't really know where to cut the line. And so a very important method to take these imperfections into account is called the optical extraction, where you simply weigh the information of the pixel with a weight factor that is essentially given by the signal to noise of the spectrum at that position. And then if you do that, you can, this is for comparison, this is a raw spectrum, and this is a spectrum extracted with this technique. You can see that many of these artifacts are gone simply because pixels that are noisy were given a very low weight, whereas the pixels that have a clear, nice spectrum, signal, that were given a high weight. Okay, then you do this, and this is, by the way, anyone knows what kind of spectrograph this might be?
From a shell to a multi-orbits.
I mean, I will give you a hint. Let's say you have a multi-object spectrograph, or where we said, well, you take fibers and then you align them, and you put the spectra all on top of each other. Right? And a smart optical designer would put them very close together. Yeah? And they would all have the same distance if your optic is right. But here we see that apparently the distance between here and here, and here and here and here and here is different. So that's some indication that we're not looking at a multi-object spectrograph, that we're looking at some spectrograph where someone used cross dispersion. Because when you do the cross dispersion, then you have the wavelength dependency of your order sphere. And so, just because, or you use the very last design. In this case, just from the signature here, you would guess already this is an HL spectrum. Yeah, and that concludes the course.
So, don't leave. Now we have the surprises for all of you. Now, okay, although this is not the end of the meeting, we have to borrow one more class by Elena. We will have also the seminar by Paulo. And we will have also the class of the micro course of airbody simulations by Carlos. Where are you going? Where are you going, Bernard? Bernard? Oh. So, and during the night at 6 o'clock, we will have all this is okay. This is a cup of coffee with a beautiful draw on the university. Okay.
My institute.
Yes. Please. You have to take picture of all my friends. You don't have to. Please. Let me see if we have flash.
Okay. So it's something that does not smell. Literally a book of 400 years of telescopes.
Oh, my friend. So
I have a special collection of the book, of course, so that's why I think
because you are
it's easy to pick it.
Yes.
But it is apart from the name on the cover, it is an excellent book. With many contributions, and they're very good.
It's in Dutch, so.
it's in Dutch. It's very good. Yes, of course. So, oh, please. This book is for you, right? This is it will be in our office, you know. So, actually, I don't know how to say protagonistas, the main characters of this meeting are you, actually. Okay, you are the bravest people here. Actually, have a confession. 20 years ago, I was in the undergraduate program at the level of Camilo, for example. And it would be impossible for me to follow any of these lectures. So actually, I was, probably I would drop out from this course. So if you are here, you are very brave. Because you know me. So, okay, I want you deserve an applause. And finally, I want a picture just of you, because you are the bravest people here in the university. Probably here. So, can we arrange the chairs and the